Imagine standing at the edge of everything that exists. Not a physical edge with a barrier or fence, but a threshold where space, time, and the laws of physics begin to break down. Picture yourself floating there, suspended between what can be known and what cannot. The familiar stars and galaxies have long since faded behind you. You are about to discover the most profound destination in our universe, the place where all journeys, if followed far enough, eventually lead. Where the maps end not because we've stopped drawing, but because drawing itself becomes impossible. This is not science fiction. This is the frontier of modern physics, where our most brilliant minds have encountered a cosmic contradiction so profound it reshapes our understanding of reality itself. What you're approaching is both infinitely dense and impossibly small. A place where time slows to a stop and space curves completely back upon itself. Tonight, we will journey toward what astronomers, physicists, and mathematicians have been studying for over a century. The mysterious objects that represent both the end and perhaps the beginning of everything we know. Black holes. The name itself carries a certain weight, doesn't it? A heaviness that seems fitting for objects so dense that not even light can escape their gravitational pull. But what is a black hole really? Beyond the dramatic name and the sensational depictions in science fiction, what truth awaits us when we approach these cosmic enigmas? Tonight, we will explore not just what black holes are, but what they mean for physics, for our universe, and perhaps most surprisingly, for our own existence. We'll trace their story from mathematical curiosities that emerged from Einstein's equations to observational realities that have been photographed by massive telescopic arrays spanning our entire planet. You may have seen the images, a glowing orange ring surrounding a dark center, but that picture tells only a fragment of the story. The reality of what we're seeing extends beyond what our eyes or even our minds can easily comprehend. Black holes represent the ultimate limit of our understanding, places where the laws of physics as we know them begin to fray at the edges and ultimately break down completely. They are cosmic question marks, challenging everything we thought we knew about the nature of reality. And yet, paradoxically, they may also hold the key to understanding it all. What happens inside a black hole? Does time itself cease to exist? Is information truly lost forever once it crosses the event horizon? Or is it somehow preserved and coded on the surface? These questions have divided the world's greatest physicists for decades. Einstein himself never fully accepted the implications of his own equations when it came to these strange objects. And yet, the evidence for their existence continues to mount. We've detected their gravitational waves, imaged their silhouettes, and observed stars orbiting their invisible presence. The journey we're about to undertake will take us from the death throes of massive stars to the centers of galaxies, including our own. The Milky Way harbors a supermassive black hole at its heart, quietly shaping the motion of everything around it. But our exploration won't end there. We'll venture into even more speculative territory: the connection between black holes and the birth of universes, the information paradox, and the holographic principle. These concepts sound like science fiction, but they emerge directly from our best physical theories, general relativity and quantum mechanics, when pushed to their limits. What makes black holes so fascinating isn't just their extreme nature. It's that they seem to exist at the intersection of the very large and the very small, the cosmic and the quantum. They force us to confront the uncomfortable reality that our current understanding of physics is incomplete. Something is missing in our picture of how the universe works. And that missing piece might just revolutionize everything we thought we knew about reality, space, time, and even our own existence. So settle in as we begin this journey toward understanding the most extreme objects in our universe. Let your mind expand as we approach the places where space and time themselves are stretched beyond recognition. The story of black holes is not just about distant cosmic objects. It's about the limits of knowledge itself, and what happens when we dare to venture beyond those limits. It's about what we find when we follow the laws of physics to their logical conclusions, even when those conclusions seem impossible or contradictory. But most importantly, it's about perspective. How understanding the most extreme places in our universe gives us a new lens through which to view our own existence. Because in the end, the story of black holes is also our story. Their matter was once star stuff, just like the elements that make up our bodies. And the physical laws that govern their behavior are the same laws that allow us to exist, to think, and to wonder about our place in this vast cosmic ocean. So join me now as we begin this exploration of the ultimate cosmic destination, the place where all paths of scientific inquiry seem to lead, if followed far enough. Tonight, we dive into the mystery of black holes, not just as objects in distant space, but as windows into the fundamental nature of reality itself. Chapter 2: Premise and Human Meaning. Why should black holes matter to us? They exist so far beyond our everyday experience, in conditions so extreme they seem entirely disconnected from human concerns. And yet, these cosmic extremes offer something precious: perspective. They show us the outer boundaries of what's possible in our universe, the edges of what can exist. When we contemplate black holes, we're not just examining exotic astronomical objects. We're exploring the fundamental rules that govern reality itself, the same rules that allow us to exist. This is the profound connection between the cosmic and the human. The laws of physics that create black holes are the same laws that create us. Consider what happens when a massive star dies. Having exhausted its nuclear fuel, the outward pressure that kept it stable falters, and gravity, the weakest of nature's four fundamental forces, suddenly becomes unstoppable. The star collapses, its matter falling inward with such ferocity that not even the forces holding apart subatomic particles can resist. Space itself bends under this tremendous concentration of mass. If the star is massive enough, nothing can prevent total gravitational collapse. The density becomes infinite, space-time curves completely, and a black hole is born. This cosmic drama might seem remote from human experience, but it reveals something essential about our place in the universe. We exist in the gentle middle ground of nature's possibilities. Our bodies, our planet, our solar system, they all exist in a delicate balance between forces. Not too hot, not too cold. Not too dense, not too diffuse. Not too stable, not too chaotic. Black holes show us what happens at one extreme when gravity overwhelms all other forces. They reveal the edge of physical possibility, and in doing so, they help us understand the precious equilibrium that allows for complexity, for life, for consciousness, for all the things we value most. There's something comforting in this perspective. The universe contains these extremes, places where reality itself seems to break down, yet here we are, existing in the habitable middle. We're made from star stuff, as Carl Sagan famously noted. The elements in our bodies were forged in stellar furnaces and scattered by supernova explosions, the very processes that sometimes create black holes. This cosmic connection runs deep. The carbon in our cells, the iron in our blood, the calcium in our bones, all were created in stars that lived and died before our sun was born. In a very real sense, we are the universe becoming conscious of itself. Through us, the cosmos can contemplate its own existence, including its most extreme manifestations. Black holes also offer existential perspective. They remind us that everything is temporary, even stars that burn for billions of years. Change is the only constant in our universe. Yet there's beauty in impermanence. The brief flickering of consciousness that is human existence gains meaning precisely because it doesn't last forever. Black holes demonstrate another profound truth. Information changes form, but may never truly disappear. This principle, debated fiercely among physicists, has philosophical implications beyond science. The quantum information that describes everything that falls into a black hole might be preserved, encoded somehow on the event horizon, transformed but not destroyed. If true, this suggests a universe where nothing is ever completely lost. Changed, certainly. Transformed beyond recognition, often. But not erased from existence entirely. What does this mean for us? Perhaps that our actions, our thoughts, our very existence leaves an indelible mark on reality, subtle but permanent. Black holes also humble us intellectually. They expose the limits of our current understanding, the places where our best theories break down and point toward deeper truths we haven't yet grasped. This humility is essential to scientific progress. Acknowledging what we don't know opens the door to discovery. The quest to understand black holes has already transformed physics once, with Hawking's discovery that they emit radiation and eventually evaporate. What future revelations await as we continue to study them? Perhaps most powerfully, black holes offer a metaphor for transcendence, for passing through apparent endings to discover new beginnings. Some theoretical physicists speculate that the extreme conditions inside black holes might give birth to new universes, with new physical laws and new possibilities. If true, then what appears to be the ultimate dead end, a place from which nothing can escape, might actually be a cosmic doorway to entirely new realities. This possibility resonates with human experience. What seems like an ending often contains within it the seeds of something new, something we couldn't have imagined before. Black holes teach us that reality is stranger, more wonderful, and more profound than our intuition suggests. They remind us to question our assumptions about what's possible. They show us that the universe doesn't conform to our expectations. It continually surprises us, challenges us, and expands our conception of what exists. In this way, black holes offer not just scientific knowledge, but wisdom. They teach us to embrace mystery, to find comfort in questions without immediate answers. They remind us that we live in a universe that still has secrets to reveal, depths we have yet to plumb. And most importantly, they connect us to something larger than ourselves, the vast cosmic drama that has unfolded over billions of years, and will continue long after we're gone. This connection doesn't diminish our importance. Rather, it elevates the miracle of our existence. Against all odds, in this universe of extremes, here we are, contemplating the cosmos that created us. Chapter 3: Origins and Early Science. The story of black holes begins not with observation, but with mathematics, pure thought, exploring the consequences of physical laws stretched to their limits. Their theoretical existence emerged from Einstein's general theory of relativity, published in 1915, which described gravity not as a force, but as a curvature of space-time caused by mass and energy. Einstein's equations were so complex that even he couldn't fully solve them in all situations. It fell to others to explore their implications for extremely dense objects. Just months after Einstein published his theory, the German physicist Karl Schwarzschild found a solution describing the space-time around a perfectly spherical mass. Schwarzschild was no armchair theorist. He derived his solution while serving on the Russian front during World War I, shortly before his death from an autoimmune disease in 1916. His mathematics revealed something profound. If enough mass were concentrated in a small enough region, the curvature of space-time would become so extreme that nothing, not even light, could escape. This boundary, the point of no return, would later be called the event horizon, and the distance from the center to this boundary became known as the Schwarzschild radius. For a mass like our Sun, this radius would be just under 3 kilometers. For Earth, less than a centimeter. The more massive the object, the larger its Schwarzschild radius. But these were just mathematical curiosities at first. Even Schwarzschild didn't believe such objects actually existed. Einstein himself resisted the idea, searching for reasons why nature would prevent such extreme collapse. The term black hole wouldn't enter scientific vocabulary until 1967, when American physicist John Wheeler coined it during a conference lecture to replace the more cumbersome, gravitationally completely collapsed object. Before then, these theoretical entities were known by various names: dark stars, frozen stars, or collapsers. Wheeler's term captured their essential nature and quickly became standard. But long before scientists had mathematics to describe them, people gazed at the night sky and wondered about darkness. Ancient mythologies around the world contained stories of cosmic voids and places of no return. The Mayans described a dark rift in the Milky Way as a road to the underworld. Norse mythology spoke of Ginnungagap, the yawning void that existed before creation. While these weren't scientific descriptions of black holes, they reflect humanity's long-standing fascination with cosmic darkness and the unknown, the places beyond our perception. The scientific journey continued in 1939, when Robert Oppenheimer and his student Hartland Snyder calculated that massive stars could collapse catastrophically at the end of their lives. Their paper, on continued gravitational contraction, described how a star's core might collapse to a singularity, a point of infinite density where the known laws of physics break down. This work connected stellar evolution to the possibility of black hole formation. But it came just as World War II was beginning, and physics would soon be diverted to other urgent matters. After the war, theoretical work on gravitational collapse continued, but many physicists still considered black holes mathematical artifacts rather than real objects that could exist in nature. A key breakthrough came in the 1960s, when new astronomical observations revealed quasars, incredibly bright objects at cosmic distances that outshone entire galaxies. The enormous energy output of quasars defied explanation until theorists proposed that they might be powered by supermassive black holes at the centers of galaxies, actively consuming surrounding matter. This began a shift in thinking. If black holes could explain these observations, perhaps they weren't just theoretical curiosities, but actual components of our universe. The 1960s also saw the discovery of neutron stars, incredibly dense stellar remnants where a teaspoon of matter would weigh billions of tons on Earth. These confirmed that nature could produce extraordinarily compact objects. If neutron stars existed, perhaps even more extreme objects, black holes, could exist too. Meanwhile, theoretical work continued to explore the strange properties of these hypothetical objects. In 1963, New Zealand mathematician Roy Kerr found solutions to Einstein's equations for rotating black holes. Kerr's work was crucial because real astronomical objects rotate. His mathematics showed that spinning black holes would drag space-time around them like a whirlpool, an effect called frame dragging. Around the same time, Soviet physicists Yakov Zeldovich and Igor Novikov developed some of the first detailed models of matter falling into black holes, predicting the formation of superheated accretion disks. These disks would become key to detecting black holes indirectly. If we couldn't see the black holes themselves, we might see the glowing matter spiraling into them. By the late 1960s, the theoretical foundation for black holes was solid. But a crucial question remained. Did they actually exist in nature, or were they merely mathematical possibilities? The answer would begin to emerge in 1971 with the launch of the Uhuru satellite, the first space telescope dedicated to X-ray astronomy. Uhuru discovered several powerful X-ray sources that appeared to be paired with normal stars in binary systems. One in particular, Cygnus X1, would become the first strong black hole candidate. Observations showed a blue supergiant star orbiting an invisible companion that was too massive to be a neutron star. The intense X-rays suggested matter from the visible star was falling onto something extremely compact. By 1974, most astronomers accepted that Cygnus X1 contained a black hole, the first compelling evidence that these objects weren't just theoretical constructs, but real cosmic entities. That same year, Stephen Hawking made a theoretical breakthrough that would transform our understanding of black holes and challenge their very definition. Combining general relativity with quantum mechanics, Hawking predicted that black holes should emit radiation due to quantum effects near the event horizon, a phenomenon now called Hawking radiation. This meant black holes weren't completely black after all. More importantly, it meant they would slowly lose mass and eventually evaporate entirely. Though this process would take unimaginably long for stellar mass black holes, Hawking's work revealed a profound connection between gravity, quantum physics, and thermodynamics. Black holes, it seemed, obeyed the laws of thermodynamics just like any other physical system. Chapter 4. First Evidence and Scale. If you were to approach a black hole, your first indication of its presence would not be visual. You would feel it before you could see it, its gravitational influence extending far beyond its dark silhouette. This is how astronomers first detected black holes, not by seeing them directly, but by observing their gravitational effects on visible matter and light. The first confirmed black hole, Cygnus X1, revealed itself through its interaction with a companion star. Gas from the companion forms a superheated accretion disk as it spirals toward the event horizon. This disk reaches temperatures of millions of degrees, emitting X-rays that our telescopes can detect. It's like identifying an invisible predator by watching its prey being consumed. Throughout the 1980s and 1990s, astronomers discovered more X-ray binary systems containing likely black holes. Each discovery strengthened the case that these objects were real cosmic features, not just theoretical constructs. But stellar mass black holes, formed from collapsed stars, represent only one category. A far more massive variety lurks at the centers of galaxies. The evidence for these supermassive black holes began to accumulate in the 1990s, as astronomers used the Hubble Space Telescope and ground-based observatories to peer into galactic cores. They discovered something remarkable. Stars near the centers of galaxies were orbiting at tremendous speeds around seemingly empty space, clear evidence of an enormous yet invisible mass. Nowhere was this more apparent than at the center of our own Milky Way, where a radio source called Sagittarius, * resides, 26,000 light-years from Earth. By tracking stars orbiting Sagittarius * for over 16 years, astronomers calculated that this invisible object contains about 4 million times the mass of our Sun, concentrated in a region smaller than our solar system. The precision of these measurements earned Andrea Ghez and Reinhard Genzel the 2020 Nobel Prize in Physics. Their work provided the most compelling evidence yet for supermassive black holes. But how do we comprehend the scale of these objects? Let's start with stellar mass black holes, TYPICALL, containing 5 to 100 times the mass of our Sun. Despite their enormous mass, their event horizons are remarkably small, about 30 kilometers across for a 10 solar mass black hole. You could drive across one in less than half an hour if it weren't for the inconvenient fact of being torn apart. The gravitational gradient near a stellar mass black hole is so extreme that it would stretch your body like taffy, a process colorfully termed spaghettification by scientists. Your feet, closer to the black hole and thus experiencing stronger gravity than your head, would be pulled with significantly more force, stretching you vertically while compressing you horizontally. Supermassive black holes tell a different story. The one at the center of our galaxy has an event horizon roughly 25 million kilometers in diameter, about 1/6 the distance from Earth to the Sun. Counterintuitively, the gravitational gradient around such an enormous black hole is less extreme. You could potentially cross the event horizon without being torn apart, though what happens next remains theoretically contentious. The largest known supermassive black hole, at the center of the galaxy TUN 618, contains an estimated 66 billion solar masses. Its event horizon would encompass our entire solar system out to Pluto. These cosmic leviathans pose a profound question. How did they form? Stellar mass black holes have a clear origin story in the deaths of massive stars. But supermassive black holes require a different explanation. Did they grow from smaller seed black holes that merged in accreted matter over billions of years? Or did they form directly from the collapse of enormous gas clouds in the early universe? The answer remains elusive, but recent observations of quasars from the cosmic dawn, just a few 100 million years after the Big Bang, show that supermassive black holes formed surprisingly quickly in cosmic history. Black holes don't just vary in mass, but also in spin. A rotating black hole drags space-time around it like a ball spinning in honey, creating a region called the ergosphere, where nothing can remain stationary. This rotation potentially allows black holes to serve as enormous cosmic accelerators, flinging particles to near-light speeds and powering the most energetic phenomena in the universe: relativistic jets. These jets, extending for thousands or even millions of light years, are seen shooting from the cores of active galaxies. They contain particles moving at 99.99% the speed of light. In 2017, our understanding of black holes entered a new era when the LIGO and Virgo observatories detected gravitational waves from two merging black holes, ripples in the fabric of space-time itself. This monumental discovery confirmed another prediction of Einstein's theory and opened a new window for observing cosmic collisions invisible to traditional telescopes. Then, in 2019, the Event Horizon telescope collaboration released the first direct image of a black hole shadow, a dark circle surrounded by a glowing ring of superheated matter. This image showed the supermassive black hole at the center of galaxy M87, 55 million light-years away. For the first time, we could see the silhouette of an event horizon against the backdrop of its luminous surroundings. 2 years later, the same team produced an image of our own galactic center black hole, Sagittarius A*. Though closer, it's much smaller than M87's black hole, making it equivalently difficult to image. These direct observations marked a watershed moment in black hole science, transitioning these objects from theoretical entities to observable features of our universe that we could actually see. But even as we've begun to see black holes, profound mysteries remain. What happens at the singularity, where our current physics breaks down? Is information truly lost when it crosses the event horizon? These questions stand at the frontier where general relativity meets quantum mechanics, the two pillars of modern physics that, despite a century of effort, have resisted unification. Black holes seem to exist precisely at this theoretical fault line. They require both theories to describe fully, yet those theories give contradictory answers about what happens inside. This contradiction, known as the information paradox, has driven theoretical physics for decades and may hold the key to a deeper understanding of space, time, and matter. As we prepare to explore these deeper mysteries, consider the journey we've taken, from mathematical curiosities to observable cosmic entities, from theoretical speculation to captured images. Black holes have moved from the fringe of theoretical physics to the center of our understanding of cosmic evolution. We now know that far from being rare anomalies, they're fundamental components of our universe. Every large galaxy appears to harbor a supermassive black hole at its center. Our cosmic neighborhood contains countless stellar mass black holes. They shape the evolution of galaxies and the distribution of matter across the cosmos. And while we've made tremendous progress in understanding them, the deepest questions about black holes remain unanswered, questions that touch the very foundations of physical reality. What happens when you follow the path of a particle beyond the event horizon? Does space-time continue to curve until it reaches a singularity of infinite density? Or does quantum mechanics intervene, preventing infinite curvature? Could black holes be portals to other universes, as some theoretical models suggest? Might they connect distant regions of our own universe through wormholes, hypothetical tunnels through space-time? These questions aren't merely academic. They probe the fundamental nature of reality: space, time, matter, energy, and information. They ask what is ultimately possible in our universe. In the next part of our journey, we'll venture even deeper into these mysteries. We'll explore what modern physics says happens inside black holes and what that might mean for the nature of reality itself. Chapter 5: Contradictions and Paradoxes. As we venture deeper into the nature of black holes, we encounter a landscape not of certainty, but of contradiction. Here, at the extremes of density and gravity, our best physical theories begin to clash. General relativity, which describes gravity as the curvature of space-time, predicts that matter falling into a black hole continues, collapsing until it reaches a singularity, a point of infinite density. At this singularity, the equations of general relativity simply break down. They predict infinite values, which physicists take as a sign that the theory itself has reached its limit of applicability. But quantum mechanics, our framework for understanding the subatomic world, strongly suggests that infinities cannot exist in nature. Some more fundamental principle must intervene. This fundamental disagreement between our two most successful physical theories creates what physicists call the singularity problem, the first major contradiction we encounter when studying black holes. If quantum mechanics is correct, something must prevent complete collapse to a singularity. But what? Various proposals exist, from loop quantum gravity to string theory, each offering different resolutions. Some theories suggest that matter reaches a maximum density governed by quantum effects, creating a fuzzball rather than a singularity. Others propose that space itself becomes granular at the smallest scales, preventing infinite density. This isn't merely a mathematical curiosity. It speaks to the fundamental nature of space and time. Is space-time ultimately continuous, as general relativity assumes? Or is it discrete at the smallest scales, like the pixels on a screen? But the contradictions don't end with the singularity. An even more profound paradox emerges when we consider what happens to information that falls into a black hole. Quantum mechanics insists that information cannot be destroyed. The complete state of a system at one time determines its state at all future times. Information must be preserved. Yet black holes seem to destroy information. Once matter crosses the event horizon, all its distinct properties, except mass, charge, and angular momentum, appear to vanish from our universe. This contradiction creates the infamous black hole information paradox, first identified by Stephen Hawking in the 1970s and still unresolved despite decades of theoretical work. Hawking made matters more complex when he discovered that black holes emit radiation and eventually evaporate. What happens to the information contained in objects that fell in? Is it somehow encoded in the radiation? If not, quantum mechanics is wrong about information conservation. If yes, then how exactly is the information preserved and encoded? The answers remain elusive. The information paradox has divided physicists for decades. Some, like Hawking initially, were willing to accept that information might truly be lost, requiring a modification of quantum theory. Others, led by Leonard Susskind and Gerard 't Hooft, insisted that information must be preserved somehow. Their work led to the holographic principle, one of the most revolutionary ideas in modern physics. The holographic principle suggests that all the information about what falls into a black hole might be encoded on its event horizon, similar to how a two-dimensional hologram can contain the information of a three-dimensional image. This principle has profound implications beyond black holes, suggesting that our three-dimensional reality might be encoded on a distant two-dimensional surface, our universe as a kind of cosmic hologram. Another contradiction involves the fate of a conscious observer falling into a black hole. According to general relativity, they would pass through the event horizon without noticing anything special happening. From their perspective, the laws of physics would continue normally, at least until tidal forces became strong enough to cause spaghettification, the vertical stretching and horizontal compression of objects. But from an outside observer's perspective, relativistic effects would cause time to appear to slow down for the falling observer. They would seem to freeze at the event horizon, never quite crossing it. These two perspectives, the falling observer who crosses the horizon uneventfully and the external observer who never sees this happen, seem irreconcilable. How can both be correct? This has led to heated debates about the nature of event horizons. Some physicists have proposed alternatives, like firewalls, regions of intense energy that would destroy anything approaching the horizon. Others suggest fuzzballs, where the horizon is replaced by a surface of quantum states. Still others maintain that the standard picture is correct, and the apparent contradiction is just a matter of different reference frames. The contradictions extend to the very existence of event horizons. Some theoretical approaches to quantum gravity suggest that true event horizons might not form at all, replaced instead by apparent horizons that eventually evaporate. These debates aren't merely academic. They touch on fundamental questions. Is information ever truly lost? Is space-time continuous or discrete? Can the same event appear completely different to different observers? Adding to these theoretical puzzles, observations sometimes challenge our models. In 2019, astronomers captured the first image of matter surrounding a black hole, revealing the shadow of M87's supermassive black hole. While this image broadly confirmed our expectations, the details continue to be analyzed. Some features, like the exact shape and size of the shadow, depend on how gravity behaves in extreme conditions we can't test on Earth. More puzzling are observations of extremely bright quasars in the very early universe. These suggest that supermassive black holes formed much more quickly than our standard models predict. How did black holes with billions of solar masses form less than 1 billion years after the Big Bang? Did they grow from smaller seed black holes at impossibly fast rates, or form directly from the collapse of enormous gas clouds? Observations of galaxies reveal another anomaly. The mass of a galaxy's central black hole seems tightly correlated with properties of the galaxy itself, suggesting a profound connection in how they evolve. This is surprising because a supermassive black hole, despite its enormous mass, is tiny compared to its host galaxy, like a pea in the center of a sports stadium. How does it exert such influence over the entire galaxy? Perhaps the most tantalizing contradictions emerge at the intersection of black holes and cosmology. The mathematics describing black holes shows remarkable parallels with equations describing the expansion of the universe. This has led some theoretical physicists to propose that our entire universe might exist inside a black hole in a larger parent universe. Conversely, each black hole in our universe might contain an entire baby universe. Such nested cosmologies remain highly speculative, but they emerge naturally from the mathematics of general relativity when extended to its limits. Even the fate of black holes presents contradictions. Hawking's work showed that they slowly evaporate through quantum effects, but the final stages of this process remain mysterious. Does a black hole evaporate completely, leaving no trace? Or does it leave behind some remnant containing the information of everything that ever fell in? Our current theories cannot provide a definitive answer. These contradictions and anomalies aren't failures of science, they're opportunities. They mark the boundaries of our current understanding and point toward deeper truths waiting to be discovered. Throughout history, the most significant scientific advances have emerged from precisely such contradictions. Einstein's theories of relativity arose from anomalies in our understanding of light and gravity. Quantum mechanics emerged from contradictions in our understanding of atoms and radiation. The contradictions surrounding black holes may similarly lead to the next revolution in physics. What makes these cosmic objects so valuable to science is precisely their extreme nature. They push our theories to their breaking points, revealing where new physics must emerge. In the words of physicist Richard Feynman, we are trying to prove ourselves wrong as quickly as possible, because only in that way can we find progress. Black holes provide the perfect laboratory for this approach, a cosmic crucible where our most successful theories falter, pointing the way towards something even more profound. Chapter 6. Myths, Misreads, and Edge Cases. Black holes have captured the public imagination like few other cosmic objects. Their mysterious nature and extreme properties have spawned countless depictions in science fiction, from Star Trek to Interstellar. But this cultural fascination has also led to widespread misconceptions. Let's gently correct some of these myths while maintaining our sense of wonder at these extraordinary objects. Perhaps the most common misconception is that black holes are cosmic vacuum cleaners, sucking in everything around them. This image of a voracious cosmic predator stalking the universe isn't accurate. A black hole's gravitational pull follows the same laws as any other massive object. If our sun were suddenly replaced by a black hole of identical mass, Earth's orbit wouldn't change at all. We wouldn't be sucked in. We'd continue orbiting exactly as before, just around a dark point instead of a bright star. We'd freeze rather than fall into the black hole. Black holes only capture objects that come very close to them, within what astronomers call the capture radius, which is larger than the event horizon but still a relatively small region of space. Another common myth is that black holes are empty spaces or holes in the fabric of the universe. The name black hole unfortunately reinforces this misconception. In reality, black holes contain matter, often enormous amounts of it, compressed to incredible density. They aren't empty. They're the opposite of empty. The event horizon isn't a physical surface, but a boundary in space-time where gravity becomes so strong that escape becomes impossible. There's no hole there in the conventional sense. Science fiction often depicts black holes as portals to other dimensions or distant parts of our universe. While theoretical physics doesn't rule out such possibilities entirely, the scientific evidence for such connections remains non-existent. Some speculative models of black hole interiors do include wormholes, hypothetical tunnels through space-time, but these would almost certainly collapse instantly rather than provide stable passages. Even if traversable wormholes could exist, they would require exotic forms of matter with negative energy density to remain open, something we've never observed and may not exist. The depiction of black holes in visual media often reinforces misconceptions. The most common image shows a cosmic whirlpool or vortex, a flat, swirling disk leading to a central hole. Real black holes are three-dimensional objects. The accretion disks that sometimes surround them are indeed relatively flat, but the black hole itself warps space in all directions. A more accurate visual would show light bending around a spherical region of darkness, with distorted images of stars and galaxies in the background, similar to what was captured in the Event Horizon Telescope image. Time dilation near black holes is another frequently misrepresented phenomenon. Films like Interstellar correctly show that time passes differently near these objects, but often exaggerate the effect for dramatic purposes. While time does slow dramatically near the event horizon, the extreme differentials portrayed in fiction would require positioning precisely at the horizon, a precarious location, impossible to maintain in orbit. The 2014 film Interstellar deserves credit for its relatively accurate depiction of a black hole, created with input from theoretical physicist Kip Thorne. Its portrayal of the accretion disk and gravitational lensing was groundbreaking. However, even this scientifically informed depiction made compromises for visual clarity. Real black holes would appear different depending on our viewing angle and would display more extreme light-bending effects. Another common misunderstanding involves Hawking radiation. Popular accounts often describe this as black holes leaking or particles escaping from beyond the event horizon. In reality, Hawking radiation forms just outside the event horizon through quantum fluctuations in the vacuum. No information actually escapes from inside the black hole through this process. The idea that black holes will instantly tear apart anything that approaches them, sometimes called spaghettification, is only partially accurate. For stellar mass black holes, tidal forces are indeed extreme near the event horizon. The difference in gravitational pull between your head and feet would stretch you into a long, thin strand. But for supermassive black holes, like those at galactic centers, the tidal forces at the event horizon are much milder. You could theoretically cross the horizon of a billion solar mass black hole without feeling anything unusual. Of course, once inside, escape would be impossible, and you would eventually meet the singularity, or whenever quantum gravity effects replace it. Science fiction often depicts people observing events inside black holes, or communicating with those who cross the event horizon. This violates a fundamental principle. No information can escape from beyond the horizon. Once something crosses that boundary, it's causally disconnected from our universe. No signal, message, or information of any kind can return to tell us what happened. This makes direct observation of a black hole's interior permanently impossible, regardless of how advanced our technology becomes. Whatever happens inside remains hidden from external observers forever. The misconception that black holes violate the law of conservation of energy is also common. People wonder where all the mass and energy goes when it falls into a black hole. The answer is straightforward. It remains in the black hole, increasing its mass. Black holes obey the conservation laws just like any other physical system. When a black hole eventually evaporates through Hawking radiation, that energy is gradually released back into the universe. The total energy always balances. Some viral content claims that scientists don't know where matter in a black hole goes, implying some mysterious disappearance. This misrepresents scientific uncertainty about the singularity. While we don't have a complete theory of what happens at the center of a black hole, we can track its total mass, charge, and angular momentum perfectly well from outside. The mystery involves the form matter takes at the center, not whether it continues to exist. Einstein's famous equation E equals mc reminds us that mass is a form of energy. Another common misread involves scale. Popular depictions often fail to convey the truly vast differences between stellar mass black holes and their supermassive counterparts. A typical stellar black hole might have 10 times the Sun's mass concentrated in a region smaller than Manhattan. A supermassive black hole can contain billions of solar masses. The black hole at our galaxy's center, Sagittarius A*, contains about 4 million solar masses. The largest known, Ton 618, contains about 66 billion solar masses, enough to stretch from our Sun past Pluto. The media sometimes reports on black holes as threats to Earth. Stories about wandering black holes, or the Large Hadron Collider creating microscopic black holes, have generated unnecessary concern. In reality, even if a stellar mass black hole passed through our solar system, it would not swallow Earth unless it came extremely close, an astronomically unlikely event. And any microscopic black holes theoretically created in particle accelerators would evaporate almost instantly through, Hawking radiation posing no threat whatsoever. Perhaps the most profound misconception about black holes is that they represent cosmic dead ends, places where physics breaks down completely and nothing meaningful can be said. In fact, black holes have become central to our deepest theories about the nature of space, time, and information. Far from being cosmic anomalies, they may hold the key to quantum gravity. The study of black holes has led to breakthroughs like the holographic principle, which suggests a profound connection between gravity and information that extends far beyond black holes themselves. Rather than representing the end of physics, black holes stand at the frontier of our understanding, cosmic laboratories where we can test the most fundamental theories about reality itself. Chapter 7. Stakes and what changes if true. What's truly at stake in our quest to understand black holes? Why does it matter whether information is preserved or lost? Whether singularities exist, or how event horizons truly behave? These questions might seem academic, relevant only to theoretical physicists. But their answers have profound implications for our understanding of reality and potentially for our technological future. At the most fundamental level, black holes test the limits of our physical theories. If information is truly lost in black holes, then quantum mechanics, one of our most successful theories, needs revision. This wouldn't just affect our understanding of black holes. Quantum mechanics underlies our explanation of everything from chemical bonds to semiconductor physics, the foundation of all modern electronics. Any modification to quantum theory would ripple through our entire scientific understanding, potentially affecting technologies we haven't yet imagined. Conversely, if information is preserved, as many physicists now believe, then general relativity must be modified instead. Einstein's beautiful geometric theory of gravity cannot be the final word. This suggests that space-time itself, the stage on which the cosmic drama unfolds, has a more complex structure than we currently understand. It might be quantized, holographic, or emergent from something even more fundamental. Such revelations would transform our conception of reality itself. Is space continuous or discrete? Is time fundamental or emergent? Do higher dimensions exist? Black holes push us to confront these questions. On a more practical level, understanding the physics of extreme gravitational environments helps us develop and test instruments for observing the cosmos. The Event Horizon Telescope, which produced the first image of a black hole, required synchronizing atomic clocks across continents with unprecedented precision and developing new data processing algorithms. These technologies have applications far beyond black hole imaging, from improved GPS systems to better medical imaging techniques. Scientific pursuit often yields practical benefits in unexpected ways. Black holes also offer potential applications for timekeeping and navigation. Their stable properties could theoretically serve as cosmic reference points, natural celestial beacons whose properties don't change over billions of years. A sufficiently advanced civilization might use the properties of supermassive black holes to synchronize clocks across interstellar distances or as navigation beacons for spacecraft. The study of information preservation in black holes has already influenced quantum computing research. The connections between information theory, thermodynamics, and gravity emerging from black hole physics have practical applications. The theoretical work on black hole entropy by Jacob Bekenstein and Stephen Hawking established fundamental limits on how much information can be stored in a given region of space. This directly impacts our understanding of the ultimate limits of computation and data storage, questions of increasing relevance in our information-based civilization. Black holes also raise profound questions about the fate of our universe. Some models suggest that the accelerating expansion of space might eventually create a cosmic horizon with properties similar to a black hole's event horizon. If true, this cosmic horizon would impose fundamental limits on how much of the universe we can ever observe or influence, regardless of how advanced our technology becomes. Understanding black hole evaporation through Hawking radiation might provide insights into this cosmic fate. Will information be preserved if our universe expands forever? What does that mean for the ultimate legacy of intelligent life? These questions might sound philosophical, but they emerge directly from our best physical theories when extended to their logical conclusions. Beyond these scientific and technological stakes lie equally important existential ones. Black holes challenge our understanding of fundamental concepts like infinity, determinism, and the nature of time itself. They force us to consider whether our conventional notions of inside and outside, before and after, break down in extreme conditions. This has implications for how we understand causality and free will. If the information that falls into a black hole is ultimately preserved and released through Hawking radiation, then in some sense, the future knows about the past. Everything that ever falls in leaves a trace that will eventually emerge. This suggests a universe where information is never truly lost, where every event leaves an indelible mark on reality, however transformed or scrambled it might become. Such a perspective offers a kind of cosmic consolation. In a universe where nothing is truly forgotten, every action, every moment, every thought has a kind of permanence, not in its original form, but encoded in the fabric of reality itself. Conversely, if information is genuinely lost in black holes, then our universe contains true endings, places where causality breaks down completely, and the past cannot be reconstructed even in principle. This would mean that parts of our universe's history become permanently inaccessible, cosmic amnesia that erases portions of reality from the ledger of existence. Either possibility profoundly shapes how we might understand our place in the cosmos and the ultimate significance of our actions. The resolution of these questions will likely require a theory of quantum gravity, a framework that successfully reconciles general relativity and quantum mechanics, our two most fundamental but currently incompatible theories. String theory, loop quantum gravity, causal set theory, asymptotic safety, and other approaches each offer potential paths forward, but none has yet provided the complete, experimentally verified framework we seek. Black holes stand at the center of this quest, the cosmic phenomena that most clearly demand quantum gravity for their complete description. They are natural laboratories for testing any candidate theory. Some theoretical approaches suggest that the interior of a black hole might contain a bounce rather than a singularity, a transition to an expanding region that could be considered a new universe. If true, black holes could be cosmic engines of creation, places where collapsing matter rebounds into expanding spacetime, potentially giving birth to baby universes with their own laws of physics. Our own universe might have emerged from such a process in a parent universe. This speculative but mathematically supported idea would fundamentally change our understanding of cosmic origins and evolution. Such revelations would transform our understanding of creation itself. Rather than a single Big Bang, we might live in an eternally reproductive cosmos, a vast multiverse of universes sprouting from black holes like seeds from a cosmic tree. Other theoretical approaches suggest that space and time themselves might be emergent phenomena, not fundamental aspects of reality, but arising from deeper quantum entanglement structures. This perspective, inspired by the holographic principle derived from black hole physics, suggests that what we experience as space-time might be a kind of illusion, a projection from a more fundamental quantum reality. If true, this would be among the most profound scientific revelations in history, comparable to the Copernican revolution that displaced Earth from the center of the cosmos. Just as we learned that Earth is not the center of the physical universe, we might discover that space and time are not the foundation of ultimate reality. The stakes extend to our cosmic future as well. If intelligent life persists for billions of years, it will witness the evaporation of black holes through Hawking radiation, an almost unimaginably slow process for large black holes. A stellar mass black hole would take about 1,067 years to evaporate, trillions of times longer than the current age of the universe. Supermassive black holes would take even longer, about 10,100 years. These timescales dwarf our current cosmic age of 13.8 billion years. They point to a far future where black holes become the last remaining organized structures in an otherwise diffuse and cold universe. In this remote epoch, black hole evaporation might provide the only available energy source for any surviving intelligence. the last fires in a dark and dying cosmos. Understanding black hole evaporation might therefore prove crucial for the ultimate long-term survival of consciousness in our universe. A consideration that extends far beyond our immediate concerns, but speaks to the deepest questions of purpose and possibility. As we prepare to explore even deeper mysteries in our final chapters, consider how far we've come. We've traced black holes from theoretical curiosities to observational realities, from mathematical anomalies to cosmic engines. We've seen how they challenge our most fundamental theories and push us toward new conceptions of space, time, and information. We've considered their practical implications and their existential significance. But perhaps their greatest value lies in how they humble us intellectually while expanding our cosmic perspective. They remind us that reality extends far beyond human intuition, that the universe is not only stranger than we imagine, but stranger than we can imagine. And yet, remarkably, our mathematics and observations continue to penetrate these mysteries. Black holes, the most extreme objects in our universe, yield their secrets grudgingly, but steadily to human inquiry. This suggests something profound about the relationship between mind and cosmos, between the neural networks in our brains and the fabric of reality itself. That we can comprehend objects as extreme as black holes, even partially, speaks to a deep harmony between human thought and cosmic structure, a correspondence that itself deserves wonder. What remains to be discovered about these cosmic enigmas? What final revelations await as we push our theories and observations to their limits? And what will these discoveries tell us about the nature of reality itself? Chapter 8: Frontiers of Understanding. As we approach the deepest mysteries of black holes, we find ourselves at the frontier of theoretical physics. Several competing frameworks attempt to resolve the contradictions we've explored. Each theory offers a different vision of what happens at the extreme edge where space, time, and matter reach their limits. Let's explore these competing visions of reality with an open mind. The first major theoretical framework comes from string theory, which proposes that all particles and forces in nature arise from tiny vibrating strings in higher dimensional space. In string theory, black holes become comprehensible as dense collections of these fundamental strings. The approach transforms our understanding of the singularity, that troublesome point of infinite density at a black hole's center. String theory suggests there is no true singularity. Instead, the extreme conditions transform the black hole interior into a fuzzball, a tangled ball of strings with finite density and no singularity at all. This elegant solution preserves information because the infalling matter becomes part of this string configuration. When the black hole evaporates, the information encoded in these strings is gradually released. The fuzzball proposal resolves several paradoxes simultaneously. It eliminates the singularity problem, preserves information, and maintains consistency between quantum mechanics and gravity. But string theory comes with significant challenges. It requires extra spatial dimensions beyond the three we experience, dimensions that would need to be curled up extremely small to explain why we don't detect them. Despite decades of development, string theory has struggled to produce unambiguous predictions that can be tested experimentally. Its mathematical beauty remains its strongest argument, a compelling but insufficient credential in science. A competing framework comes from loop quantum gravity, which takes a different approach. Rather than adding dimensions and fundamental objects, it proposes that space itself has a discrete quantum structure. In this view, space isn't infinitely divisible, but composed of fundamental units, tiny loops of gravitational connection at the Planck scale, about 10 to 35 meters, far smaller than anything we can directly measure. Loop quantum gravity suggests that the collapse of matter in a black hole reaches a limit when these fundamental spatial units can't be compressed further. The inward collapse bounces, creating an expansion in a new region. This bounce would transform the singularity into a gateway to a new expanding region, potentially a whole new universe with its own space and time, connected to our universe through the black hole. Like string theory, loop quantum gravity eliminates the singularity, but it does so through quantum properties of space itself rather than through new fundamental objects. This approach offers a profound reconceptualization of black holes, not as cosmic dead ends, but as cosmic wombs, regions where collapsing matter seeds the birth of new cosmic domains. Loop quantum gravity faces its own challenges, however. Reconciling its discrete spacetime with the continuous Lorentz symmetry of special relativity has proven difficult, raising questions about its consistency with established physics. A third theoretical direction draws inspiration from quantum information theory. This approach focuses not on particles or space, but on information itself as the fundamental currency of reality. From this perspective, the event horizon becomes a kind of information barrier or firewall. Some physicists suggest that anything approaching the horizon would encounter intense radiation that would destroy it. This firewall hypothesis preserves information at the cost of contradicting general relativity's prediction that nothing special happens at the horizon. It's a radical solution that remains highly controversial. An alternative information theoretic approach comes from the holographic principle, which proposes that all the information contained in a volume of space can be encoded on its boundary surface. Applied to black holes, this suggests that everything falling in is completely described by quantum states on the event horizon itself. The interior volume becomes a kind of holographic projection of this boundary information. This perspective transforms how we think about space itself. Three-dimensional space may be emergent rather than fundamental, arising from more basic quantum entanglement patterns. The holographic approach has gained significant theoretical support, particularly through the ADS-CFT correspondence, a mathematical relationship discovered by Juan Maldacena in 1997 that connects gravity in curved spacetime to quantum field theory. This correspondence provides a concrete mathematical framework for understanding how gravity and quantum mechanics might be reconciled, at least in certain idealized theoretical settings. Each of these approaches, strings, loops, and holography, offers profound insights. Each resolves some paradoxes while creating new questions. Each requires us to abandon some cherished intuition about the nature of reality. String theory asks us to accept unseen dimensions. Loop quantum gravity challenges our notion of continuous space. Holographic theory suggests that three-dimensional space itself might be illusory. The most remarkable aspect isn't their differences, but their convergent suggestions. That space and time as we know them may not be fundamental, that information plays a crucial role, and that black hole interiors might connect to new cosmic domains. These convergent themes suggest we're approaching something profound, a deeper understanding of reality that transcends our current frameworks. Newer theoretical directions continue to emerge. Some physicists explore causal set theory, which models spacetime as a discrete set of events connected by causal relationships, rather than as a continuous manifold. Others pursue asymptotic safety, suggesting that gravity naturally weakens at high energies in ways that prevent singularities from forming. Still others investigate emergent gravity, where gravity results from quantum entanglement patterns. What unites all these approaches is their attempt to reconcile quantum mechanics with general relativity, our two most successful but mutually incompatible physical theories. Black holes stand precisely at the intersection where these theories clash most dramatically. They are cosmic laboratories where the very large gravity, space-time curvature, meets the very small quantum effects, Hawking radiation. This is why black holes matter so much to theoretical physics. They force us to confront the limitations of our current understanding and point towards something deeper. The quest to understand what happens inside black holes isn't merely academic. It touches fundamental questions about the nature of reality itself. Is information ever truly lost? Is space fundamentally continuous or discrete? Does time flow in only one direction? Can causes ever be disconnected from effects? The answers will reshape not just our understanding of black holes, but our conception of the universe itself. These competing theories aren't just abstract mathematical exercises. They make different predictions about black hole behavior that advanced observations might eventually distinguish. For example, they predict different patterns in the gravitational waves produced when black holes collide, or subtle differences in the radiation emitted as they evaporate. They also offer different resolutions to the famous firewall paradox identified by physicists in 2012, a seemingly irreconcilable conflict between general relativity, quantum field theory, and the holographic principle. This paradox asks whether an observer falling into a black hole would experience anything unusual at the event horizon. General relativity says no. Some quantum considerations suggest they'd encounter intense energy, a firewall. The resolution might come from realizing that these theories describe the same underlying reality from different perspectives, each capturing some aspect of the truth while missing others. This parallels the famous wave-particle duality of quantum mechanics, where light behaves sometimes as a wave, sometimes as a particle, depending on how we observe it. Perhaps black holes similarly require complementary descriptions, different mathematical frameworks that each capture part of a deeper reality our current language and concepts cannot fully express. As we await more observational evidence and theoretical developments, we must remain humble. The history of physics teaches us that our most cherished theories often give way to more comprehensive frameworks. Newton's laws, once thought complete, were subsumed by Einstein's relativity. Perhaps both quantum mechanics and general relativity will eventually be recognized as approximations of some deeper theory. What's certain is that black holes will continue to guide this quest. They remain cosmic question marks, challenging our understanding while pointing toward deeper truths about the nature of reality itself. Chapter 9. Windows into the Extreme. For centuries, black holes existed only in mathematics, solutions to Einstein's equations with no observational evidence. Today, we not only know they exist, we can see their shadows, detect their collisions, and measure their effects on surrounding matter. This transformation from theoretical to observational science continues to accelerate. New instruments and techniques are opening unprecedented windows into these cosmic extremes. Perhaps the most dramatic breakthrough came in April 2019, when the Event Horizon Telescope collaboration released the first direct image of a black hole shadow, the supermassive black hole at the center of galaxy M87. This wasn't accomplished with a single telescope, but through very long baseline interferometry, linking radio telescopes across the globe to create a virtual Earth-sized observatory with extraordinary resolution. The technical challenges were immense. Each telescope had to measure radio waves with atomic clock precision. Petabytes of data were recorded onto physical hard drives, as the information was too massive to transmit over the internet. The resulting image, a glowing orange ring surrounding a dark shadow, confirmed predictions from Einstein's theory with remarkable precision. The size and shape of the shadow matched theoretical expectations almost perfectly. 2 years later, the same collaboration imaged Sagittarius asterisk, the supermassive black hole at the center of our own Milky Way galaxy. Though much closer, it's also much smaller, presenting its own observational challenges. These direct images represent just the beginning. The Event Horizon Telescope continues to improve, adding more telescopes and higher frequencies to sharpen its vision of these cosmic shadows. Another revolutionary window opened in 2015, when the LIGO and Virgo observatories detected gravitational waves, ripples in the fabric of space-time from two merging black holes. 1.3 billion light-years away. This detection marked the birth of gravitational wave astronomy, an entirely new way of observing the cosmos that doesn't rely on electromagnetic radiation, but on the vibrations of space-time itself. Since that first detection, dozens more have followed. Each gravitational wave event tells the story of black holes spiraling together and merging, revealing their masses, spins, and even giving clues about their formation history. These observations have already yielded surprises. Some merging black holes were significantly more massive than expected from stellar evolution models, suggesting either different formation pathways or previously unknown stellar processes. The observed merger rates have also provided constraints on the total population of black holes in the universe. There appear to be more of these objects than many models predicted. Gravitational wave observatories continue to improve their sensitivity. Future detectors, both ground-based and space-based, will detect thousands of mergers each year, creating a census of black holes throughout cosmic history. The James Webb Space Telescope, launched in December 2021, provides yet another window. Its infrared vision can peer through cosmic dust to observe the environments around supermassive black holes in unprecedented detail. Webb can study the relationship between black holes and their host galaxies across cosmic time, helping resolve questions about how these enormous objects formed and grew in the early universe. It can also observe quasars, brilliantly glowing black holes actively consuming matter from the cosmic dawn when the universe was less than 1 billion years old. These observations challenge our understanding of black hole formation. Finding billion solar mass black holes when the universe was just 5% of its current age raises profound questions about how they grew so quickly. X-ray observatories like NASA's Chandra and ESA's Newton provide complementary views. They detect the extremely energetic radiation produced when matter heats to millions of degrees before crossing the event horizon. These X-ray observations reveal the dynamics of accretion, how matter flows into black holes, and the powerful jets that some black holes launch from their poles, extending for thousands of light years. Future X-ray missions with even greater sensitivity and resolution will map the spinning disks of matter around black holes in unprecedented detail, potentially testing predictions about how space-time curves in these extreme environments. Neutrino observatories offer yet another avenue. These elusive particles interact so weakly with matter that they can escape from regions where even light is trapped, potentially carrying information from close to the event horizon. The IceCube Neutrino Observatory at the South Pole has already detected high-energy neutrinos from active galactic nuclei, galaxies with supermassive black holes actively consuming matter and launching powerful jets. Future neutrino detectors may capture neutrinos from even more extreme environments, providing a unique probe of physics near the event horizon that complements electromagnetic and gravitational wave observations. This multi-messenger approach, combining light across the electromagnetic spectrum with gravitational waves and neutrinos, provides a more complete picture than any single method could offer. Each messenger carries different information. Light shows us the environment around black holes. Gravitational waves reveal their masses and spins. Neutrinos might eventually tell us about processes near the horizon itself. Together, these complementary observations are testing general relativity in stronger gravitational fields than ever before. So far, Einstein's century-old theory has passed every test with remarkable precision. But tiny deviations from general relativity's predictions might reveal the first clues to quantum gravity, the long-sought theory that would reconcile Einstein's framework with quantum mechanics. New paradoxes continue to emerge as our observations become more precise. Recent studies of the black hole shadow in M87 reveal subtleties not fully captured by classical general relativity. The exact shape and size of this shadow depends on whether and how quantum effects modify the event horizon, a question at the heart of theoretical debates about firewalls, fuzzballs, and holography. Another emerging puzzle comes from observations of gravitational waves. The mergers detected so far show no obvious deviations from general relativity, but the ring-down phase, when the newly formed black hole settles into its final state, holds clues about its nature. This ring-down can be decomposed into characteristic oscillations called quasi-normal modes. The precise pattern of these modes could reveal whether the object has a true event horizon or something more exotic. The apparent lack of echoes in gravitational wave data currently favors the standard picture of black holes with event horizons, but more sensitive future detections might reveal subtle deviations. Meanwhile, computational advances allow increasingly sophisticated simulations of black hole physics. These numerical models reveal the complex dynamics of merging black holes and accretion processes impossible to calculate analytically. Quantum computing may eventually allow us to simulate quantum gravity effects near black holes, calculations far beyond the capabilities of classical computers. As our observational and computational tools advance, the gap between theory and observation continues to narrow. Ideas that once seemed permanently confined to mathematical speculation now face empirical testing. This empirical grounding is essential for scientific progress. No matter how mathematically elegant a theory might be, it must ultimately conform to observational reality to be considered valid. The next decade promises remarkable advances. The Laser Interferometer Space Antenna, LISA, planned for the 2030s, will detect gravitational waves from supermassive black hole mergers across cosmic history. Next-generation ground-based gravitational wave detectors will capture thousands of black hole mergers each year, creating a demographic profile of these objects throughout the universe. Extremely large telescopes, with primary mirrors 30 meters or larger, will resolve the dynamics of gas and stars around supermassive black holes with unprecedented clarity, testing predictions about how space-time curves in strong gravity. These observations may finally distinguish between competing theories of quantum gravity by revealing subtle effects predicted by one framework but not others. The convergence of observation and theory marks a golden age in black hole physics. What began as mathematical curiosities has become empirical science, a remarkable transformation within a single human lifetime. Chapter 10. Beyond the Horizon. We've journeyed from the mathematical discovery of black holes to their observational confirmation, from theoretical paradoxes to cutting-edge instruments. Now it's time to address our central question: where does space travel ultimately lead? The answer emerges from everything we've explored. All paths through space, if followed far enough, eventually lead to black holes, cosmic inevitabilities that represent both the end and perhaps the beginning of space itself. This isn't merely poetic language. It reflects profound physical principles about the nature of gravity, space, time, and the evolution of our universe. Consider the cosmic long view. Our universe began in an extremely hot, dense state, the Big Bang, and has been expanding ever since. Galaxies formed, stars ignited, planets coalesced. But this cosmic history isn't simply a story of expansion. It's also a story of gravitational clumping, matter gathering together under gravity's persistent pull, forming ever more complex structures. This dual process, cosmic expansion and gravitational clumping, creates the rich tapestry of our universe. But what happens in the very long term, over trillions of years? Current observations suggest that our universe will continue expanding forever, driven by mysterious dark energy. Galaxies will recede from each other at an accelerating rate, eventually becoming invisible to one another. Stars will exhaust their nuclear fuel. Planets will spiral into dead stellar remnants or be flung into interstellar space. The universe will grow increasingly cold and dark. But gravity never stops working. Even in this cosmic twilight, matter continues to clump together. And when enough mass concentrates in a small enough region, the inevitable result is a black hole. Over vast timescales, years and beyond, quantum tunneling will cause particles to occasionally fall into these isolated black holes, gradually increasing their mass. Eventually, most matter in the universe will either be locked in black holes or exist as diffuse radiation, too spread out to ever regurgitate. The universe becomes a scattered collection of black holes in an otherwise empty void. Even these black holes aren't eternal. As Stephen Hawking discovered, quantum effects cause them to emit radiation and slowly evaporate. Larger black holes persist longer, but all eventually disappear. A stellar mass black hole takes about 1,067 years to evaporate, trillions of times longer than the current age of the universe. Supermassive black holes might last 10,100 years or more. But eventually, after timescales so vast they defy intuition, even these cosmic leviathans dissipate into radiation. The universe approaches a state of maximum entropy, a diffuse soup of photons and other particles at nearly uniform temperature. This heat-death scenario represents our best current understanding of the universe's ultimate fate. And black holes play a central role in this cosmic story, as the final repositories of organized matter before the ultimate dissolution. But this isn't the only possibility. Recent theoretical work suggests black holes might hold an even more profound position in cosmic evolution. Several quantum gravity approaches suggest that the interior of a black hole doesn't end in a singularity, but transitions to an expanding region, potentially a whole new universe with its own space and time. This possibility, arising from different theoretical frameworks, including loop quantum gravity and certain string theory scenarios, transforms black holes from cosmic dead ends to cosmic generators. In this view, each black hole might seed the birth of a new universe, with physical properties partly inherited from its parent universe, but potentially varied through the equivalent of cosmic mutation. Our own universe might have formed this way, emerging from a black hole in a parent universe. And the black holes in our universe might be giving birth to daughter universes, inaccessible to us but continuing the cycle of cosmic evolution. This scenario, sometimes called cosmological natural selection, suggests a kind of multiverse driven by an evolutionary process. Universes that produce many black holes generate many offspring universes. If true, it would mean that all paths through space not only lead to black holes within our universe, but potentially through black holes to entirely new universes with their own space and time. The mathematics supporting this possibility emerges naturally from attempts to reconcile quantum mechanics and general relativity. It's not just speculation, but a consequence of following our best theories to their logical conclusions. Even if this specific scenario proves incorrect, black holes clearly represent something profound, the ultimate destination of matter under gravity's influence, and potentially the seeds of new cosmic domains. This perspective transforms how we understand cosmic evolution. Rather than a linear process from Big Bang to heat death, we might live in an endlessly creative cosmos, a vast, branching tree of universes sprouting from black holes. Each universe would have its own space and time, causally disconnected from its parent once formed. The full structure would be a multiverse more vast and varied than even our most ambitious cosmic visualizations. What makes this scenario so compelling is that it emerges not from mystical thinking, but from hard-nosed attempts to resolve contradictions in our most successful physical theories. It also addresses deep questions about our universe's apparent fine-tuning. If cosmic reproduction through black holes exists, then universes might naturally evolve physical constants conducive to black hole formation. And since stars, the progenitors of many black holes, require the same physical conditions that enable life, this cosmic evolutionary process might explain why our universe seems hospitable to complexity and consciousness. This remains speculative, but represents a frontier where cosmology, black hole physics, quantum gravity, and even concepts analogous to biological evolution converge in unexpected ways. Whether or not black holes literally birth new universes, they certainly represent the ultimate cosmic destinations, the final state toward which matter inevitably evolves under gravity's influence. They also represent the frontiers of our understanding, places where space, time, matter, and information reach their limits and point toward deeper principles we're only beginning to grasp. In answering our central question, where space travel ultimately leads, we find not a simple endpoint but a profound transition. Black holes represent both the ultimate destination and potentially the ultimate beginning. This circular journey, where endings become beginnings, mirrors patterns we observe throughout nature. From the water cycle to the carbon cycle to the stellar cycle that created the elements in our bodies, the cosmos repeatedly transforms endings into new beginnings. Black holes may represent this principle at the grandest scale, cosmic engines that recycle reality itself, transforming collapsed matter and space into new domains of possibility. So the next time you gaze at the night sky, remember that you're not just looking at stars and galaxies. You're looking at a cosmos filled with these extraordinary objects, places where space and time reach their limits. And in those limits, we find not just an ending, but perhaps the seeds of cosmic renewal, the ultimate expression of a universe that appears designed not for stasis, but for creative evolution. This is the profound revelation at the heart of modern black hole physics. All paths through space eventually lead to these extraordinary objects. And they may not be cosmic dead ends, but cosmic gateways, thresholds to new domains of reality. As we complete our journey through the extreme physics of black holes, we're left with a paradoxical insight. These darkest objects in our universe have illuminated our understanding of reality in profound ways. They've revealed that space and time are not immutable, but can bend, warp, and perhaps even transform into something entirely new. They've shown us that information, while it may be scrambled, might never be truly lost. They've suggested that our universe might be one leaf on a vast cosmic tree, connected through black holes to domains we can never directly observe, but can infer through mathematics and theory. Most importantly, they remind us that human understanding, while limited, can still penetrate the deepest mysteries of existence. Through observation, mathematics, and theory, we've glimpsed realities far beyond ordinary experience. This journey never truly ends. Each answer opens new questions. Each horizon reveals new vistas. The cosmos invites endless exploration, both outward through telescopes and inward through mathematics and contemplation. Perhaps that's the ultimate comfort these cosmic extremes offer. In a universe of beginnings and endings, where even black holes eventually evaporate, something remains constant: the beautiful patterns that underlie reality and our ability to perceive them. As you drift towards sleep, consider that you're part of this cosmic story. The atoms in your body were forged in stars. The laws that govern black holes also govern your dreams. We are the universe contemplating itself. Join us again as we continue to explore the profound mysteries of our cosmos, from quantum realms to cosmic horizons, from ancient starlight to future possibilities. Subscribe for more journeys into the beautiful patterns of reality that surround us and sustain us.